Welcome to Physics Made Easy channel. And the next topic that we are picking up from nuclei is isotopes. We have just finished with very elementary topics like nuclear size, nuclear density, and now the topic of isotopes. Isotopes, atoms of an element which have same atomic number, but they have got different mass numbers. Their mass numbers are different. Different mass numbers are called isotopes. Such atoms contain the same number of protons and electrons but different number of neutrons. The basic difference lies in number of neutrons. Because of their small electronic sizes, isotopes. Now, they have got same number of protons and same number of electrons and different number of neutrons. Now their electronic configurations are similar. Because of their similar electronic configuration, they exhibit similar chemical properties. Isotopes exhibit similar chemical properties because of their same or similar electronic configuration. So here I have got some examples of isotopes, and before going through examples, let me settle the screen. This is the properties, and they occupy same position in the periodic table, and we have got the examples. Examples are hydrogen 1H1, then 1H2 is deuterium and 1H3 is tritium. Now they have got same number of protons, and this hydrogen is having one proton and one neutron, and this deuterium is having one proton and one neutron, and this is having only one proton. This is having one proton and two neutrons, and their configuration is 1H1, 1H2 and 1H3. Now if you see all these three, their electronic configuration is same. That's why they exhibit similar chemical properties. And now we have got 2 helium-3, 2 helium-4, 2 helium-6. They have got similar chemical properties because of similar electronic configurations. And the difference lies only in number of neutrons. And on the same lines, we have got 6 carbon 10, 6 carbon 11, 6 carbon 12, 6 carbon 13 and 6 carbon 14. They have got same number of protons and hence same number of electrons, same electronic configuration, similar chemical properties, but may possess different nuclear properties. Next is isobars. Isobars have same mass number but different atomic numbers. Same A is same mass number, different atomic numbers, and hence different number of neutrons and protons. And we have got the classical examples. They occupy different positions in periodic table, and then we have got some examples of isobars. For example, 1H3, 2H3, see there, A number is same, 3 and 3, and then 16S37 and 17 chlorine 37. Now 37 is same, A is the same, and we have got different Z. Now in all these cases, A is same and we have got different Z. For example, here it is 37, here it is again 37, 3 and 3, and then 11 sodium 22, and then 10 neon 22. Now mass number is same, atomic number is different, number of protons and neutrons they are different. Then calcium and argon, mass number 40, atomic number 20 and 18. The next example is isotones. Isotones, they have got same number of neutrons are called isotones. For example, 17 chlorine 37, 20 neutrons. 19 Potassium 39, 20 neutrons, and then 1H3, 2 neutrons, 2H4, 2 neutrons, same number of neutrons, 8O16, 8 neutrons, 6 carbon 14, 8 neutrons, they are isotones. They have got the same number of neutrons. And the next in position is one or two more examples. For example, 4 beryllium 9, 5 neutrons, 5 boron 10, 5 neutrons, 6 carbon 13, 7 neutrons, 7 nitrogen 14, again 7 neutrons. Then we have got 11 sodium 23. It has got 12 neutrons, 12 magnesium 24. It is again having 12 neutrons. And next is isomers. Isomers are, these are the nuclei with same atomic number and mass number but existing in different energy states. Now they have got everything same. What same? Same atomic number, same mass number, but existing in different states. For example, a nucleus in ground state is identical in metastable excited states are. For example, a nucleus in its ground state and an identical nucleus in its metastable state. They are isomers. And then famous mass energy relationship. Einstein first to establish the equivalence of mass and energy through the famous mass energy relationship. E is equal to mc square. C is the velocity of light. So this relationship is known for this fact that mass can be converted into energy and energy can be converted into mass. And mass and energy, they are equivalent. So rest mass energy E naught is equal to m naught c square. E is equal to mc square is rest mass energy plus kinetic energy. Note this fact. Note this fact. This E, this is simply a very important fact, and we cannot afford to ignore it. Now, we have got the concept of rest mass energy E naught is equal to m naught c square. M naught is the mass of an object when it is at rest. Now suppose the object acquires velocity v, its mass becomes m naught into 1 minus v square c square. Now its new energy E, this will be mc square according to equation number 2. And let kinetic energy of the body be T. Then we can conveniently write this relationship that E is equal to E naught plus kinetic energy T, or kinetic energy T is equal to E minus E naught. From here we will fill the value of T, E and E naught. E is mc square minus E naught is m naught c square. So this T is m minus m naught into c square. Now note down the concept of relativistic kinetic energy. Note this fact very clearly. So T is delta m into c square. So kinetic energy in relativistic mechanics is change in mass multiplied by square of velocity. And in classical mechanics, kinetic energy is equal to half of mass into velocity square. Note down these two differences. Kinetic energy in relativistic mechanics. This I call relativistic mechanics or relativistic mechanics, where bodies move with velocity of light, velocity comparable to velocity of light. In relativistic mechanics, we have got Kinetic energy is equal to change in mass multiplied by square of velocity of light. And in normal mechanics, this is in mechanics, you will, in work power energy, you will have gone through this concept even in your 10th, 9th or 10th classes, that kinetic energy is half of mass into velocity square. This formula is applicable in non-relativistic mechanics, means in which the velocity of the bodies is much lesser than the velocity of light, as it is in our daily life. So in daily life, half mv square formula will be applied. But when you are talking of the motion of electrons or protons inside a nuclei or inside a gas, then if their velocity is comparable to the velocity of light, then the formula for kinetic energy will change and T will be delta m c square. Again, listen, delta m is change in mass. Now, there were two different laws of conservation of energy and law of conservation of mass. This relationship E is equal to mc square has united the law of conservation of mass and energy, and a new law came into being, and that is law of conservation of mass energy states. The sum of mass energy of a system or particle is same before and after an interaction. This is the formal statement, and we shall be making use of this statement repeatedly. And now, mass defect. This is a very important concept from examination point of view. All the three examinations, whether it is NEET, JEE Main or your board examination, the concept of mass defect is very important. What is mass defect? The difference between the rest mass of nucleus and some of the rest masses of nucleons forming the nuclei in free state is called mass defect. So this mass defect, concept of mass defect is very important. Listen once more. The difference between the rest of nuclei, the difference between the rest mass of nuclei and some of the rest masses of the nucleons forming the nuclei in free state is called mass defect. Now, mass defect, rest mass of the nucleus and the sum of the rest masses of the nucleons forming the nuclei in free state is called mass defect. Now, ZXA. Now, in this case, A is mass number. Now, the number of protons, I will like to say NP, will be equal to Z. Number of neutrons, NN, they will be equal to mass number minus Z. Now, let m be the mass of proton. Let m be the mass of proton, as he says, m mass of proton, mn mass of neutron, m capital N is mass of nuclei. So now mass defect is delta m represented by delta m. It will be equal to mass of the nucleus. This is the mass of the nucleus. And first there are m protons. Protons means Z. I will take MP. And I will write here MP. So things will be clear. So this is the mass of protons, and we will add up mass of neutrons. A minus Z are the total number of neutrons multiplied by mass of neutrons. This minus rest mass of the whole nuclei. So this is the mass defect. And this mass defect is mostly in the unit of AMU. And also note that 1 AMU, if you have to directly convert into energy, this will be 931 million electron volts. So this is mass defect. And now, if we have to calculate energy corresponding to it, that will be E, and that will be delta M into C square. Now, if I substitute the value of delta M, if I substitute the value of delta M, then E will come out to be ZMP is the total mass of proton, MP is mass of one proton, Z is the total number of protons, plus A minus Z is the total number of neutrons. It is multiplied by mass of a single neutron minus mass of the whole nuclei, that is made up of Z protons and A minus Z neutron. This multiplied by C square. It gives us binding energy. This much nuclear energy is responsible for binding the nuclei. And now, mass defect. Mass defect that appears in the form of binding energy is responsible for binding the nucleus together. This is responsible for binding the nuclei together. Binding energy of the nucleus is defined as the energy. Now note this definition, it is important from theory point of view. The binding energy of the nucleus is defined as the energy required to break up the nucleus into constituent proton and neutrons. First, breaking up the nuclei, plus, this line is very important, separating them to such a large distance that there is no interaction between them. First, breaking up the nuclei into its constituent nucleons. Nucleons means proton and neutrons. The first step is breaking up. The very first step is breaking up. Second step is separating. Separating them. These two are the important facts that these two are the important components of binding energy, or the important constituents of binding energy. And now we shall proceed in the similar way as we have done just a few minutes ago. So first we will calculate the mass defect that we have just calculated. The mass defect I will write again for your practice. First of all, write a nuclei ZXA, and just remind that Z is the number of protons, and then that is NP. I am denoting them by NP, and A minus Z is the number of neutrons. I am denoting them by N. And now mass defect delta M. This mass defect is number of protons Z multiplied by mass of proton MP, plus, so this is the mass of all the protons in free state, plus A minus Z is the number of neutrons, multiplied by mass of neutron. So this is the total mass of nucleons in free space. Now I will subtract the mass of nuclei from it. So this gives me mass defect. And if we have to find out energy corresponding to it, and that energy is delta M into C square. We have just done it a few minutes ago. And now in the next part, I shall be writing the binding energy of an atom. Now we are going to write here the binding, this relationship I have just written above. So this is the binding energy of an atom. This is mZxa. So this is mass of the nuclei. For example, this is the MnZxa. This stands for the mass of the nuclei plus mass of Z electrons and minus binding energy of electrons divided by C square. So this relation we kept in mind. And now we also know that mass of hydrogen atom Mh is equal to mass of proton plus mass of electron minus binding energy per nucleon. Now we again focused on the top relationship and we ignored this binding energy per nucleon. We know that Mh is Me, Mp plus Me. This is mass of hydrogen atom is Mp plus Me. And now what I did in my previous relationship, I broke up the mass of nuclei this into this minus Mn. It was already there. I added Z number of neutrons. Note down it here and note down the previous this equation. This equation, mass of neutron, mass of nucleus, sorry. The mass of nuclei which now this is I just subtracted Zmn and added Zmn. So that led us to this equation after substituting the values. And this part I will cover in my next lecture, this particular part. And you just remember up to this part here. So this is the mass defect. This is the mass of nuclei. So in the mass of nuclei, with these words I have finished this lecture, and if you like this video, kindly share it. If you don't like, then kindly comment so that we can improve our videos. Thank you very much for being with us for 20 minutes.